Yes, there are maximum length considerations for conduit and feeders from the meter to the panel, although not a directly specified maximum length in the way some might expect. The primary concern dictating practical length limitations is voltage drop. Voltage drop refers to the decrease in voltage that occurs as electricity travels along a conductor. This decrease is due to the inherent resistance of the wire. The longer the wire, the greater the resistance, and consequently, the greater the voltage drop. Excessive voltage drop can cause several problems. Firstly, it can lead to inefficient operation of electrical equipment. Motors may run slower, lights may dim, and electronic devices may malfunction. Secondly, significant voltage drop can overheat conductors and connected equipment, potentially creating a fire hazard. Thirdly, appliances are designed to operate within a specific voltage range, for example, plus or minus 5%. Significant voltage drop can cause the voltage supply to the appliance to fall outside of this range, leading to premature failure and voiding warranties. The National Electrical Code, or NEC, addresses voltage drop in informational notes to sections 210.19 A1 and 215.2 A3. These notes recommend limiting voltage drop to no more than 3% in branch circuits and 5% in feeders for a total voltage drop of no more than 5% to the furthest point of utilization. While these notes are not mandatory requirements, they represent good engineering practice and are widely adopted to ensure efficient and reliable electrical systems. Feeders carry power from the service equipment, such as the meter and main panel, to branch circuit panels or subpanels. Branch circuits extend from the branch circuit panel to the final point of utilization, like lighting outlets or receptacle outlets. The cumulative voltage drop through both the feeder and the branch circuit should ideally remain under 5%. Several factors influence voltage drop, including conductor length, conductor size, conductor material, current, and operating temperature. Longer conductors will have greater voltage drop. Larger conductors, meaning those with a greater cross-sectional area, have lower resistance and therefore less voltage drop. Copper conductors have lower resistance than aluminum conductors of the same size and length, resulting in less voltage drop. Higher current flowing through a conductor will result in greater voltage drop. Higher operating temperatures increase the resistance of conductors, leading to increased voltage drop. To determine the appropriate conductor size for a given feeder length and load, voltage drop calculations must be performed. These calculations involve using Ohm's law and considering the factors mentioned earlier. Several online voltage drop calculators and software tools are available to simplify these calculations. The calculation itself is as follows. Voltage drop equals current times resistance. This can be represented as volts D equals I times R. In practical application, you would use a more complete formula that takes into account the length of the conductor run. The NEC provides formulas and tables to assist in voltage drop calculations. For example, the formula for single-phase circuits is voltage drop equals 2 times K times Q times I times D divided by circular mils, where K is the direct current constant, which is typically 12.9 ohms for copper and 21.2 ohms for aluminum. Q is a constant that adjusts for alternating current impedance, which is usually 1 for circuits operating at less than 600 volts. I is the current in amps, D is the one-way distance in feet, and circular mils is the cross-sectional area of the conductor. For three-phase circuits, the formula is voltage drop equals the square root of 3, or approximately 1.732 times K times Q times I times D divided by circular mils. Here's a simplified overview of how to address the voltage drop concerns. Firstly, determine the load requirements. Calculate the total current that the feeder will need to carry. Secondly, determine the acceptable voltage drop. Aim for a maximum of 3% voltage drop in the feeder, keeping in mind the overall 5% target when combined with the branch circuits. Thirdly, measure the length of the feeder run from the meter to the panel. Fourthly, select a conductor size and material. Start with a reasonable conductor size, such as 4 American wire gauge or AUG copper, and adjust as needed based on calculations. Fifthly, perform the voltage drop calculation using the appropriate formula and the chosen conductor size. Sixthly, evaluate the results. If the calculated voltage drop exceeds the acceptable limit, increase the conductor size and recalculate. If the calculated voltage drop is within the acceptable limit, the conductor size is likely adequate. In cases where the distance between the meter and the panel is exceptionally long, several strategies can be employed to mitigate voltage drop. Firstly, increase the conductor size. Using a larger conductor will reduce resistance and voltage drop, but it also increases cost. Secondly, use copper conductors. Copper has lower resistance than aluminum, so using copper conductors can reduce voltage drop, but this option is more expensive. Thirdly, increase the supply voltage. If feasible, increasing the supply voltage, for example, from 120 volts to 240 volts, will reduce the current required to deliver the same amount of power, thereby reducing voltage drop. This may require different equipment. Fourthly, install an intermediate panel. Installing a subpanel closer to the load will shorten the feeder run and reduce voltage drop. Fifthly, use parallel conductors. For very large loads, running multiple conductors in parallel can effectively increase the conductor size and reduce voltage drop. However, this requires careful planning and adherence to NEC requirements. The NEC provides specific requirements for the installation of conductors in conduit. These requirements cover conductor sizing, fill capacity, and support. Firstly, conductor sizing. The NEC specifies minimum conductor sizes based on the ampacity, or current carrying capacity, required for the intended load. The ampacity of a conductor is determined by its size, material, insulation type, and the ambient temperature in which it is installed. NEC Table 310.16 provides ampacity ratings for various conductors under specific conditions. It's crucial to select conductors with sufficient ampacity to handle the load without overheating. Secondly, conduit fill. The NEC limits the number and size of conductors that can be installed in a conduit. This is to prevent overheating and ensure that conductors can be easily pulled into and out of the conduit. NEC Chapter 9, Table 1 provides conduit fill requirements based on the type and size of the conduit and the conductors being used. Exceeding the allowable conduit fill can lead to overheating and difficulty in future maintenance or modifications. Thirdly, conductor support. Conductors must be properly supported within the conduit system to prevent strain on terminations and to maintain proper spacing. The NEC specifies requirements for supporting conductors based on the size of the conductors and the type of conduit being used. Improperly supported conductors can sag, rub against the conduit, and potentially damage the insulation, leading to shorts or ground faults. Conduit types commonly used for feeders include rigid metal conduit, or RMC, intermediate metal conduit, or IMC, electrical metallic tubing, or IMT, and rigid polyvinyl chloride conduit, or PVC. RMC is a heavy-duty conduit made of steel or aluminum. It provides excellent physical protection for conductors and is suitable for both indoor and outdoor applications. RMC is the most expensive of the common conduit types but offers the highest level of protection. IMC is a lighter weight version of RMC, also made of steel. It provides good physical protection and is less expensive than RMC, making it a popular choice for many applications. EMT is a thin-walled conduit made of steel or aluminum. It is lightweight and easy to install, making it a cost-effective option for many indoor applications. EMT is not suitable for direct burial or locations where it may be subject to severe physical damage. PVC is a non-metallic conduit made of rigid polyvinyl chloride. It is lightweight, corrosion-resistant, and easy to install. PVC is suitable for direct burial and applications where resistance to moisture and chemicals is important. However, it is less resistant to physical damage than metal conduits. When installing feeders and conduit, several best practices should be followed to ensure a safe and reliable installation. Firstly, properly size the conduit and conductors. Use the NEC guidelines to determine the appropriate conduit size and conductor size for the intended load and voltage drop requirements. This will prevent overheating and ensure efficient operation. Secondly, use approved fittings and connectors. Use only fittings and connectors that are listed and labeled for the specific type of conduit and conductors being used. This will ensure a secure and reliable connection. Thirdly, properly support the conduit. Support the conduit at intervals specified by the NEC to prevent sagging and damage. This will maintain the integrity of the conduit system. Fourthly, avoid sharp bends. Minimize the number of bends in the conduit run and avoid sharp bends that can damage conductors during installation. This will facilitate easy wire pulling and prevent insulation damage. Fifthly, use pulling lubricant. Use a listed pulling lubricant when pulling conductors through long conduit runs to reduce friction and prevent damage to the insulation. This will make the installation easier and more reliable. Sixthly, properly ground the conduit. Ground metal conduit according to NEC requirements to provide a path for fault current and prevent electrical shock hazards. This is a critical safety measure. Seventhly, seal conduit ends. Seal the ends of the conduit to prevent moisture and debris from entering, which can corrode conductors and fittings. This will prolong the life of the conduit system. In Burbank, Illinois, local amendments or interpretations of the NEC may exist, so always consult with local electrical inspectors or building departments to ensure compliance with all applicable codes and regulations. These local rules can sometimes be more stringent than the NEC itself. Also, ensure all work is performed by qualified and licensed electricians.